If your P95 latency is high, caching is tempting and dangerous. We'll build a semantic cache in Redis that speeds retrieval without serving yesterday's answers. You know the pain. Users wait, models cost money, and naive caching returns stale facts. By the end, you will understand how to store and query embeddings in Redis, and how to gate hits by content version so caches stay correct. I'm Professor Pi, teaching search and IR with simple Python. Many teams reach for Redis when they need ultra-low latency and simple operational plumbing. A semantic cache stores vector embeddings alongside answers, so you can return a relevant response instantly when the query matches cached content. Success looks like sub-second lookups for common queries and a clear strategy to avoid serving outdated content. At a high level, we embed both queries and documents. Store the document vectors in Redis. Then nearest neighbor search finds the best cache candidate. The trick is to treat the cache like a retrieval layer, not an authoritative source. That means storing a version tag with each cached item, so we can detect staleness. We will build a tiny demo. It creates a RediSearch vector index, a deterministic toy embedding function, inserts a cache item, queries for the nearest cached entry, and finally gates the hit by a version field. This shows the mechanics without the noise of a real model. First, we prepare Redis for vector keys. This snippet creates a RediSearch vector index in Redis for semantic cache lookups. We connect with redis-py and call R-execute command to run FT.CREATE, targeting hash keys under the SCQ prefix. The schema defines a single vector field named vec using HNSW with 16 float32 dimensions and cosine distance. This prepares Redis to store and search vector embeddings as part of cache entries, enabling nearest neighbor retrieval. Increasing dim improves representation capacity, but must match your embedding function. HNSW generally offers fast recall for top K queries. The printed result confirms the index is ready for vector searches. Next, we add a tiny embedding function to keep the demo deterministic. This snippet defines a tiny deterministic embedding function for strings. The function emb turns text into a length D list by hashing with SHA-256 and mapping bytes to floats, then normalizes the vector for cosine distance. It returns an array of float32 values that match the Redis vector field type. This acts as a stand-in for a real embedding model, so we can focus on cache mechanics. Increasing D increases representational capacity, but must match the index dim you created earlier. The printed result shows the produced vector length, confirming the function's output shape. Now, we'll write a cache entry into Redis to simulate a stored answer. This snippet writes a single semantic cache item into Redis. We generate a unique key with INCR, compute an embedding with emb, and store it as a binary float32 blob under the vec field. The res field represents the cached retrieval answer, and ver tracks the content version to detect staleness later. Using RHset with mapping keeps the write concise and schema-friendly for RediSearch. If you standardize fields like res and ver, you can evolve cache logic without changing storage. The printed key confirms a new cache entry was inserted. Next, we query for the nearest cached embedding to show a hit path. This snippet queries Redis via RediSearch for the nearest cached embedding. We call r.execute command with FT.search using a KNN1 clause on @vec, passing the query vector as a param. Width scores returns the distance for the top match, and lower means more similar under cosine distance. Because we queried with the same text used to insert, the distance is effectively 0, demonstrating a perfect semantic hit. Increasing K retrieves more candidates, trading off latency for recall. The printed score shows the best match distance, indicating a ready cache hit path. Finally, we demonstrate gating to avoid stale answers when content changes. This snippet prevents stale cache hits by gating on a content version. We search Redis with FT.CREATE to get the nearest neighbor and return the ver field for the top result. The variable hit checks if the stored version matches the current corpus version, here assumed to be v2. Since our inserted entry is v1, the check fails and we treat it as a cache miss, even though the vector matches. If you update the entries ver to v2, this flag flips to true. Gating avoids wrong results when content changes. The printed flag explains whether the cache is safe to use. To map this toy to production, swap the deterministic emb for your model of choice and scale the index and RAM proportionally. Use an ANN strategy like HNSW for sub-millisecond top K on tens of thousands to millions of vectors. Keep a small metadata blob for each entry so you can gate on version, source ID, or TTL without touching the vector index. Recap: it is a Redis-powered semantic cache that stores embeddings and answers together. Use it when you need very low latency for repeated or common queries and when you can tolerate approximate recall. One caveat: embeddings alone do not prove currency, so always gate by a version or validate upstream before serving authoritative data. Next step: tune the index dim and the K parameter for your workload to balance representation capacity against lookup latency and recall. If you want more practical retrieval tactics, subscribe and watch the IR videos.